first introduced to problem solving in 2 dimensions, we used an example where an object was flying off of an elevated surface purely horizontally. But what happens if an object starts its motion at an angle when it's not purely horizontal? The process doesn't change, but let's look at an example of an object that does not start with a velocity in only one direction, but rather one that's at an angle. So the problem we're going to look at goes like this. On the Apollo 14 mission, astronaut Alan Shepard hit a golf ball with a 6-iron. The free fall acceleration on the moon, so this is when he was on the moon, is about 1/6 of that is on the Earth. So it's about 1.6 meters per second squared. Suppose he hit the ball with a speed of 25 meters per second at an angle of 30 degrees above the horizontal. How far did the ball travel? Now I'm going to warn you, your book gives you an equation that looks at range. This is really what is the range of this projectile if it's launched at the same level as it lands. But I don't want you to use that equation, okay? I don't want you to rely on a range equation. This is just 2-dimensional motion, and we can solve the problem using the same process that we use for anything. And so let's focus our attention on the general 2-dimensional motion process instead of remembering details and special cases, all right? So that's the outline we're going to follow. So what is the object that we're interested in? Well, the object whose motion we care about is the golf ball. Then we want to define its initial and final, what starts the motion and what ends the motion, just like we always have. The initial, it starts when the ball is hit and it begins to move. It ends when the ball hits the ground. So after it flies through the air and then subsequently lands on the ground. Okay, we're dealing with an object moving both horizontally and vertically, so this is a 2-dimension problem, but it is only a single object. And when we think about 2 dimensions, we think about motion both horizontally and vertically. And I'm just going to remind you that the time of the motion horizontally is the same as the time of the motion vertically. It's defined by this initial and final here. And so we're only going to think about a single time in this example and all examples moving forward. All right, so let's draw a picture. Here is our golf ball. It's on the ground. It's being shot at a velocity of 25 meters per second at an angle of 30 degrees. Now, I need to identify, I just want to make sure that's correct. Yep. I need to identify the origin, not just vertically, but horizontally. Not 2 of them now, horizontal and a vertical origin. So let's set the horizontal origin at the location of the ball, where anything to the right of where the ball is located is positive and anything to the left of where the ball is located is negative. Similarly, I'm going to set the vertical origin. Also, I'll make it messy, at the starting location of the ball, where everything above that origin is positive and anything below that location is negative. All right, so I have my origins, both horizontal and vertical. Time to look at my knowns. My knowns both in the horizontal direction and the vertical direction. So I have an initial position horizontal, final horizontal, initial velocity, final velocity horizontal, acceleration horizontal, and time. And notice I'm not putting the horizontal subscript on time because I've already reminded us that time is the same. There's only a single value. Similarly, for the vertical direction, I will have an initial vertical position and a final vertical position, an initial vertical velocity, final vertical velocity, and acceleration in the vertical, and again, that time that is not direction dependent. So what is my initial horizontal position? Well, my ball starts at 0. My final horizontal position, I don't know. It's not given in the problem. I do expect it to be a positive non-zero, though, if that is what I end up solving for to answer the question, because the object's moving to the right as I've drawn it. My initial velocity horizontal. The object's moving at 25 meters per second, but it's moving up and to the right. If I want to think about the horizontal velocity, then I need to think about the component of that velocity in the horizontal direction. Similarly, I will do the same for the vertical direction, the component of that velocity in the vertical direction. How do I get that? Well, this is just our vector trigonometry. So if I want this component, it's adjacent to my angle. So my horizontal component is equal to the velocity times the cosine of the angle. So in this case, 25 times the cosine of 30. And 25 times the cosine of 30 is equal to 21.7 meters per second. So my initial horizontal velocity is 21.7 meters per second. Now, this object is in two-dimensional projectile motion. It's in free fall. And so in free fall, we know our acceleration in the horizontal direction is 0, which tells us our final horizontal velocity is also 21.7 meters per second. And we don't know the time. All right, vertically, what do we have? Well, our initial position vertical is 0. The ball's going to go up and fall back down, land in the same spot vertically, so the final position is also going to be 0. Our initial vertical velocity, well, the ball's going 25 meters per second, but it's going up and to the right. So only a portion of that 25 is the up portion, and like we did for our horizontal component, we need to use the proper trigonometry for our vertical component. So in this case, that'll be 25 times the sine of 30, which should be 12.5 meters per second. Our final velocity is not given in the problem. Some of you might be able to intuit what it is, but in this particular example, we're going to say it's not given. In all cases, it might not be that easy to intuit. We do, however, have a prediction about it. The object's going to be moving down at that point. It's coming back towards the ground, so we know that it's going to be a negative non-zero, if that indeed is what we hope to solve for. Acceleration. This is in free fall. We're not on Earth, so our acceleration is at negative 9.8, but that is given in the problem. The magnitude of the acceleration is 1.6 meters per second squared. Now, that's what's given, the magnitude. We need to keep in mind that acceleration has a direction. Just like the acceleration due to gravity on Earth is always downward, the acceleration on the moon is also downward. We might intuit that because we know that this ball is going to start to rise up and slow down till it reaches a peak, and then it's going to come down and speed up. Both cases would indicate for us that we have a negative acceleration. All right, and then the time, of course, we don't know, just like before. So here's our list of knowns for each dimension, and now we have to decide what answers our question. It asks how far does the ball travel? Well, that's going to be information that we will get from our final position. So looking at our final position relationship that we have, x final, well, that's what we want to know. So this is really x final in the horizontal that we're interested in. X initial is 0. V initial is 21.7 times time plus 1/2 0 times time squared. And this term goes to 0 since we're multiplying by a 0. So simplifying this relationship, we end up with 21.7 time. Ooh, that means I need t. I need the time. I'm not given the time in the problem. I'm not able to solve for that time in the horizontal dimension, but remembering that our time is related to that vertical dimension. And so if I look at all the rest of the stuff I know, I don't know V final or the final velocity in the vertical direction, and so I'm going to use the same relationship for position to get me to my time. X final is 0, X initial is 0. V initial, 12.5 t plus 1/2 negative 1.6 times my time squared. And now I can solve for time. I end up with negative 12.5 t equals 1/2 1.6 is negative 0.8 times t squared. So my time is equal to 12.5 divided by 0.8 time is equal to 15.6 seconds. Now I have my time, and I can use that in my relationship. So 21.7 times 15.6, that gives me range of 339.1, but 339 meters. Not too bad of a golf swing for astronaut Shepard. All right, so same process as we did with one-dimensional motion. We double our work, 2 origins, 2 lists, oftentimes 2 equations to solve, recognizing that the time links these 2 lists and recognizing that the velocity given in this example is only a piece of the total of the velocity for each of the 2 dimensions. So the velocity given has to be broken up into those components. All right, good job.